Okay, so hi there. In this video, we're going to start our module 1, the first module, shall we say the chapter 1 of our number theory. This is one major subject for those taking up mathematics, and I will call this first module as fundamental properties and preliminary considerations. Okay, so the outstanding German mathematician Carl Friedrich Gauss, who lived around 1777 to 1855, once said, mathematics is the queen of the sciences, and arithmetic the queen of mathematics. So arithmetic, in the sense of which Gauss said, is number theory, which along with the geometry is one of the two oldest branches of mathematics. Number theory as a fundamental body of knowledge has played a pivotal role in the development of mathematics, and we will see in the chapters and modules ahead, in the lessons ahead, that the study of number theory is elegant, beautiful, and of course for us mathematicians and those mathematics teachers also considered as delightful. Okay, so number theory, generally speaking, is the study of the properties of numbers where when you say numbers, we mean integers, and more specifically, we really mean the positive integers. Okay, so when we say positive integers, so we solely denote that as our um, z. So again, the general term for our integers is a z, but let's try to go back with a real number. So we'll call that as the reals. Our real numbers, let's call that the reals denoted by the double script r. Okay, that's the first. When we look at algebra, when we take up algebra, we're going to be solely introduced by these real numbers. Next, in under the real numbers, we have the rational numbers. Let's call this the rationals, denoted by our q, double script q. And then alongside with the irrationals, we have what we call the irrationals, denoted by our double script q complement, because it's the complement of the rational numbers. Um, Down this rational numbers, we know that our irrational numbers there's no, um, there's no a level down below the irrational numbers, but there's a level down the rational numbers, because the rational numbers are, what do you call that, consisted of the set of our z. This is our z, the z denoted by their integers. This is the set of the integers and union the non-integers. The integers, as we will know it as numbers which are whole, meaning in the terms of the way it was constructed, it's not in a fraction form. So z complement is the one which is in fraction form. And then we will introduce ourselves with the integers. Okay, this is denoted by our double script z. Okay, and these integers are consisted by our negative integers. Let's denote that by z minus, union our 0, union our z positive. This z positive, this z plus is our positive integers. This is our 0. This is our negative integers, the z minus. Okay, so what are the integers? The integers is the z is equal to our numbers from the negative infinity. Let's start with negative 2, negative 1, 0, up until 1, 2, and then move on to positive infinity. So this is the set of our integers. We will say that one element, say, will have, for example, the integer 2 is an element, sorry, is an element of our z if 2 is inside our z. So we read this as 2 is an element of z, or in short, we can say that 2 is in z. Okay, 2 is in z. We can also take as an example as elements 3, 4, 5. Okay, these elements are also in z. Okay, since they are integers. We can also say that 1/2 is not in z, and we denote that by this symbol, the e, the in element with a cross. Okay, it is crossed. Well, we denote it without the cross if it is inside. Okay, let's further um, expound this. We say that we have another set. We will call this as the set of um, whole numbers when it is denoted by our 0 and our positive integers only. Okay, so this is the set of our whole numbers, W, double script W. And we can say Z positive can also be written as double script N. Double script N meaning these are the natural numbers or the counting numbers. It's just the same when we say that it's the positive integers, and we denote them as starting with 1, that is without the 0. So 1, 2, 3, 4, until positive infinity. So this is our definition for our integers, our positive integers specifically. This is also known as our counting numbers, our natural numbers, and these are the numbers inside that set. If we're going to combine 0 with this set, we call that the whole numbers. And if we're going to combine negative integers, that's gonna be the complete set of integers. Okay, and then so on. Again, as highlighted, we will solely focus ourselves in the study of number theory in positive integers most of the time, if not all. Okay, so that's it. Let's talk about our first important thing that we're going to talk about here. This is called the order relation. So the order relation, let A and B be elements inside, let A and B be integers in short. So then A is less than B if there exists a certain X, um, also in Z, specifically Z positive, such that, sorry, such that um, when we put when we add X to A, it's equal to B. Okay, so that is um, if B minus A is gonna be in the set of positive integers. Okay, sorry. Let's start this sentence with the word let. Okay, so mathematical writing, right? So let A and B be integers. So therefore, we can say that A is A is less than B, meaning in quantity B is greater than A. If there exists some X in the positive integers, such that if we're going to add that X to this A, it's equal to B. Okay, meaning B is greater in quantity because it is A added by X, and X is a positive integer. So we can say that it's bigger than A because B is something added to A. That is, A plus X equals B. Therefore, we can say that A is indeed A is less than B, or B is greater than A. That is, if when we have B minus A, if we're going to minus B, if we're going to have B minus A, it's still gonna be inside the positive integers since we have X is in integers. Notice that if we're going to minus A from B, it's going to be equal to X by transposing this A to the other side. So we have X equals, sorry, X equals B minus A. So since X is inside integers, so we can say that B minus A is also inside integers. Okay, so we can also say that if A is less than B, it's also equivalent of saying that B is greater than A. Okay, so that's it. Now, from this, it follows by definition that the integer A in the positive in the set of positive integers, okay, it should be strictly inside the set of positive integers, if and only if A is greater than 0. Okay, so since we know the positive integers must be starting from 1, 2, 3, 4, 5, so therefore we can say that A is inside the set of positive integers if and only if A is greater than 0. That's trivial. Okay, so after this we will be given the law of trichotomy. Let me write this down. Law of trichotomy. Sorry, should be a C here. Trichotomy. What does this law say? This says that for any given any A and B in the positive integers, there are three possibilities. There are three possibilities. Okay, excuse my handwriting. So it's going to be either, for the three possibilities, so by the law of trichotomy, if we're given a pair of positive integers, it's only going to be A is less than B, or A is just equal to B, or finally A is greater than B. There's no other choice other than these three. So the law of trichotomy states that straightforwardly. We can also combine the less than or equal to symbols. So we can say, for example, if A is less than B, at the same time A is equal to B. So we can combine the symbols. We can simply write A is less than or equal to B. Similarly, we can write the symbol um, sorry, A is greater than or equal to B if and only if, which means implies that A is greater than B, or A is equal to B. Sorry. Okay, so that's our order relation. So let's have a taste of our very first theorem in this subject. So let's state this formally. Theorem. So the theorem states that let the minimum, let min of x, y denote the minimum sorry of the integers x and y. Okay, so every time we see this notation min xy with the braces, we say that this is the minimum value of the integers x and y, and we also denote the same max of x y be their maximum. Okay, then we therefore say that the minimum of xy plus the maximum of xy is equal to x plus y. Okay, so this is our first theorem in this course. So let the minimum of x, y denote the minimum of the integers x and y, and the max x, y be their maximum. Then, when we add the minimum of x, y and the maximum of x, y, the answer is x plus y. So let's prove this by cases. Okay, so let's prove this by cases. So we have two cases here. So we're going to write this as case 1 and case 2. So case 1. Okay, case 1, say we'll have an x wherein this x is less than or equal to y. So therefore, if this x is less than or equal to y, then we can say that the minimum of this pair of values x, y is equal to x. Okay, since x is less than or equal to y. So therefore, the minimum is clearly x. And the maximum, sorry, and the max is, so if x is the minimum, the maximum is clearly going to be y. Okay, so from here, we could state that the minimum, sorry, the minimum of xy plus the maximum of xy is equal to x plus y. So that's our case 1. Clearly, if x is less, again, I'm going to read it again. If x is less than or equal to y, then the minimum of xy is equal to x, since x is less than y. And the maximum, of course, since we have two variables, the maximum is y. So therefore, the minimum of xy, which is x, plus the maximum of xy, which is y, is equal to x plus y. Clearly. And for the case 2, let's prove the otherwise. So in our case 1, we can see that we have let x is less than or equal to y. In our case 2, we will let x this time to be strictly greater than y. So if x is strictly greater than y, then we can say that the minimum of xy is equal to y. Let me write it here. Sorry. And the maximum of xy is equal to x. Okay, so again, x is greater than y, so therefore the minimum, since we have two variables, so the minimum should be y this time, and the maximum is x. Okay, so clearly we can see that in this case, the minimum of xy plus the maximum, the max of xy is equal to x plus y. Okay, so therefore from by case 1 and case 2, by case 1 and 2, by cases, shall we say 1 and 2, the proof, the theorem holds. This is our end of proof. Okay. Um, Just a remark before we end this video, a remark, a theorem, by the way, before I forget. A theorem, when you say a theorem, okay, a theorem is a major result that can be proven from from known results. Usually we write a proof for it. Well, most of the time we know that we can write a proof for it so that we can answer the theorem that it is always true. So again, theorems are always true. If it is not true, it's still called a conjecture. Okay, so we're still on page number 3 here. I think this is a good time to end the video. Okay, see you on the next video then.